Good afternoon, ladies and gentlemen. I would like to present our contribution with the title Surface Notch Orientation and Fatigue Strength of S-Built Laser Powder Bed Fusion Aluminum Alloy. This presentation was prepared in the cooperation between University of Žilina, University of Parma, and Institute of Physics of Materials, Academy Science of Czech Republic. Laser powder bed fusion is a highly complex geometries are created directly from the 3D CAD model. The process uses a high-power laser and scanner system to fuse fine metal powder layer by layer to create fully dense part. Fully automatic process that allows part to be finished in hours and without any tooling. Here is the scheme. I don't go to details because it was many presentation. Here are some examples of applications. Fatigue related to the issue is that laser powder bed fusion materials exhibit usually comparable tensile strength properties as conventionally prepared material, but fatigue properties as it is fatigue life and fatigue limit are often worse, and they are negatively influenced by surface roughness typical for additive manufacturing materials. The surface quality is influenced by many laser powder bed fusion processing parameters, such as laser power, type of scanning, layer thickness, etc. Aim of this study was experimental investigation of fatigue notch sensitivity of S-powder laser beam finish aluminum alloy to different notch orientation with respect to the build direction using a new test methodology. Notched components are important application of metal additive manufacturing, but little information is available for the part designers. Aspects to examine are experimental determination of notch fatigue life, notch surface profile characterization, and influence of quality of the notch surface on fatigue life. Chemical composition of aluminum alloy according to the standard is shown here. Atomized powder of aluminum alloy with a granulometry in the 21 to 65 microns range. Mean size is 37 microns. Application are due to the high strength to weight ratio of aluminum alloys is a good choice for automotive, aerospace, and automation application, notably gearboxes, engine parts, ductwork, heat exchanger, and etc. Here we can see a system used for fabrication specimen. This was this kind of machine SLM solution 280. Specimen were prepared in partner company BMIG in Fornavotaro in Italy. Ytterbium fiber laser wavelength of 1075 nanometers. Max laser energy was 350 watts, and layer thickness was 50 microns. Here we can see miniature specimens for fatigue test. This is a special specimen design prepared by Professor Nicoletto from University of Parma. The specimens are small, so here are these sizes which are used for the specimen production. There was used cyclic plane bending with R ratio equal to 0. Frequency was 20 Hz, and notch stress concentration factor was KT equal 1.63. Here we can see mini specimens for orientation, A minus, A plus, B and C, and applied cyclic landings is shown on this picture. This is the scheme of individual testing. Here we can see microstructure corresponding to this each orientation. So type A minus, A plus, or also type C are similar because they are vertical. And for orientation of specimen B, this is the microstructure as we can see on this slide. Here we can see some microstructure details. We can see this melt pool microstructure. There is a fine zone. This is here on the scanning microscope microstructure. Then we can see boundary of melt pools, and if we do scanning microscope high magnification, we can see quartz zone and also high affected zone. In the microstructure there are some pores and also some micro-shrinkages, but not very much, so, but they are every time present. Here we can see at small magnification detail of the notch, and this is the type B. Here we can see that it's flat. When we see this specimen C orientation, we can see that this is good roughness, but here is very low roughness. Very high roughness. So this is detail of this part. And this upskin and downskin, which is shown on the type of A plus and A minus, corresponds to this explanation how it is built the notch. So quality of notch is changed with the direction of build orientation. So here we can see compare the notch compared from type A plus, it means upskin, and downskin, which is A minus. So the quality is here very low, as you can see on the detail, especially for type A. It's the good roughness. So here we can see some curves of as-built AlSi10Mg specimens, and from this we can see that the best behavioral has the orientation B, then A plus and A minus are lower, then these are also comparable to the direction C, and from this we can see that A minus are the worst properties, the worst fatigue life. Here is some summary of performed study. And we can see from the B orientation the highest fatigue life, and it's going down with change of orientation A+, C and A-, and so we can see how change the quality of the notch surface. And from this presentation we can conclude that the orientation of notch with respect to the build direction has a large effect on fatigue life in the high cycle region. Factor 2 for the life 10 to 6 cycles. Notch orientated perpendicularly to the build direction shows good surface quality and the highest fatigue strength. Down skin notch orientation leads to very poor surface quality and the lowest fatigue strength compared to the upskin notch orientation with higher fatigue strength. The miniature specimen approach is suitable for the quantitative investigation of the as-built notch fatigue behavior of laser powder bed fusion materials. Thank you for your attention.
Thank you, Ms. Konečná. From the audience, is there any question? Yes, please.
Thank you. Have you done any study on the microstructural defects related to the poor surface quality on the walls behaviors?
In this study, it's interesting only roughness of the surface, in this case, surface on the bottom of notch. So defects don't play because there are not many. So this is technology which was improved in this company.
Yes, please.
Thank you for your presentation. I saw differences in roughness profile.
Yeah.
Either I missed it or you didn't present fatigue data.
I present some curves and there were fatigue data. So if you want, I can show it. It's here. Yeah. It's okay to show? Or?
Yeah, no, that's fine.
No. Okay.
Just if I make a comment that in all the work we have seen synergistic effect of defects and roughness. I think the statement that defects don't play a role.
No, I didn't say that they don't play. In this study, the most important is the roughness of the surface which is under loading.
Yeah, I understand that,
yeah.
But at the same time, I think defects need to be looked at to see if their population is different, if their characteristics are different.
There is also, I don't know, I didn't say this, that there are contours. Excuse me. Here you can see these contours. Yes? And if defect is here, doesn't play the main role in this testing because the loading is concentrated on this place.
There are no defects there?
You can see, yes, they are, but so small that they have no mean influencing.
Yeah, I think we can move on to another question and continue this discussion afterwards. Is there any small question?
It's enough.
I had just one very small question about the SN diagram that you presented.
Yes.
May I ask if you have any idea about why the type B is showing so much more scattered in the data compared to the other cases?
Because each specimen which you test can have some higher or lower roughness. You cannot say that each specimen, from this direction, the direction is the same.
Yeah.
So,
Yes, clearly, but the issue is that the scatter is a
but
lot higher than the other
yeah,
one.
I agree, but
So it would be good to check probably the surface, the fracture surface, to see if there has been
exactly.
any possible defect.
But we studied, but only on the flat specimens, not in the notch. So this we have to do. Yes. So
Thank
it's
you.
not
Very interesting presentation. Thank you again.